Hello friends, welcome to the course Essential of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. Now, in this lecture we are going to begin with a new probability density function which is called as normal distribution. Well, this is one of the most popular probability density function which is used in statistics. And as a statistician, if I can assume or I can verify that my observations are coming from the normal distribution, my face becomes like this, very happy, because it has got very nice statistical properties and which helps us a lot. And this distribution function has got enormous application which helps lots of people, and particularly the data scientists, because data scientists are usually working with a large number of observations, and this distribution gives us a possible way out so that we can compute many things very easily when there are complications due to the large number of observations. So, the first question comes, so what are the different applications in which this normal distribution can be used, or how this normal distribution comes into picture? Although if you remember that when we were trying to discuss about skewness and kurtosis, I had given you a brief idea. So, now this is the point where I am going to talk about the normal distribution. So, now let us try to consider a very realistic situation, and for that situation we try to plot a curve, that how the curve of that situation will look like. Now, means at our home my mom is cooking some vegetable curry. So, salt is going to be a very important ingredient in the Indian food, and particularly in a vegetable curry. So, now I try to observe the relationship between the quantity of salt and the taste of the vegetable curry. What happens when there is zero salt, there is no salt? Then the taste under normal usual conditions, we say the taste is not good and it is 0. Then what we try to do? Then we try to increase the quantity of the salt in the vegetable curry. What happens? Then we try to take the taste of the curry and we say that yes, the taste is getting better. Then we keep on adding the salt, and then a limit will come where the taste will become optimum. And after that, if you try to increase the salt, then the taste is going to be, taste will start becoming bad, I would say. And then finally, if you increase the salt beyond a certain quantity, possibly the vegetable curry will not be eatable also. So, now if you try to observe this process, what will happen? We have somewhere here the taste which is where it is maximum. So, now what we try to do? On the x axis I try to take the quantity of salt, and on the y axis I am trying to take the taste. So, now as the taste for 0 salt is 0, so we begin at 0 0. Now, the quantity of the salt is increasing, the taste is increasing, then at some point it becomes the maximum, and after that it decreases. So, can you observe we are getting here a shape like a bell? Have you seen the bell in a temple or at various religious places? They are of this shape, that if you try to cut them in the middle part, both the parts are going to be symmetric. So, that type of curve, do you think that are we going to get? Well, there can be small variation, I am not going into that part, but in general that we expect. So, now similarly there can be many things in nature that are trying to follow this type of curve, which are first increasing and then they are decreasing, and if the nature of increment and decrement, they are the symmetric around the maximum value or the mean value, then we have a bell-shaped curve. Now, the question is this: how to mathematically describe this bell-shaped curve? So, for that we have the probability density function of normal distribution, which can describe the shape of the curve with two parameters, mean and variance, that is mu and sigma square. So, let us begin our discussion on the normal distribution and we try to understand. Okay, so now we come to our slides. Okay, so the normal distribution is one of the most important distribution which are used in statistics. The name was given by Carl Friedrich Gauss, and he was a German mathematician, astronomer, geodesist and physicist, who observed that measurement in geodesy and astronomy randomly deviate in a symmetric way from their true values. So, that is why this normal distribution is also often called as Gaussian distribution. And the most widely used model for the distribution of a random variable is possibly the normal distribution. You will see in the forthcoming lecture that why it is so popular there, because anything which has got more utility, that becomes more popular. So, now the question is, what is the probability density function of a normal distribution? So, a random variable x is said to follow a normal distribution with the parameters mu and sigma square if its probability density function is given by this mathematical function. So, we are trying to write down here f x mu sigma square, and in general we will write it briefly as say f x, means as long as we are understanding the normal distribution chapter. So, that is 1 upon sigma root 2 pi exponential of minus 1 upon 2 sigma square into x minus mu whole square. And here the range of x lies between minus infinity and infinity, mu is lying between minus infinity, and sigma square, that is a positive quantity. So, this is between 0 and infinity. And we try to write this distribution as x follows normal mu sigma square like this. So, this is the probability density function of a normally distributed random variable x. Now, in case if you try to do a small algebra, that is not difficult at all, that is my promise to you. You can find out the mean value of x and variance of x. So, they come out to be as mu and sigma square. So, means I can say that the parameter mu which is involved in the PDF of a normal distribution, mu is trying to give us an idea about the mean value of the distribution, and sigma square is the variance of x, right. So, this sigma square will give us the variability of the normally distributed random variable x, right. So, this expected value of x equal to mu determines the center of the probability density function, and the value of variance of x sigma square determines the width, because I will try to show you, right. But before that there is a very important result. In case if you try to take this mu to be 0 and sigma square to be 1, then x is said to follow a standard normal distribution. Remember one thing, this is very important, and this is the distribution which has made the utility of this normal distribution a lot. So, obviously, the probability density function of a standard normal distribution is given by, just try to substitute mu equal to 0 and sigma square equal to 1 in this PDF, and then you will get here like this. F x is equal to 1 upon square root of 2 pi exponential of minus x square by 2, and x is lying between minus infinity and plus infinity. And we write it x follows normal 0 1. Right. Okay. So, now we try to understand what this mu and sigma are trying to indicate. So, in case if you try to plot the PDF of normal mu sigma square, then it will look like this, what is given here by this black line, right. And here in this case you can see that the curve is symmetric, means if you try to see around this line, right, you can see here that in this part and this part the curve is symmetric. That means if you try to take this curve and try to cut it down here and try to fold it, both these sides will be overlapping to each other. Now, in this case, this point in the middle, this is actually mu, and this part here, this is spread on the left and right hand side of this mu, which is here the orange line. This is indicating the value of sigma. For example, if you try to take a value here, mu minus sigma on the left hand side of mu and mu plus sigma on the right hand side of the mu, then this blue area is going to cover the area between the limits mu minus sigma and mu plus sigma. So, I am sure that this may remind you of something. Sometimes we call about 1 sigma limit, 2 sigma limit, 3 sigma limits, etc. So, these are the same thing. For example, mu plus minus sigma is the 1 sigma limit, and you can see here that around this central line, the area under the curve on the left hand side is 50% and the area under the curve on the right hand side is 50%. And at here, I will use here a different color pen. At here you can see this is here the maximum point. So, the curve starts here, it goes here, it reaches maximum and then it comes down, and here on somewhere there will be minus infinity and plus infinity. Right. So, what you can observe here that the density curve is symmetric and bell shaped, density is symmetric around mu, and the points of inflection of this density are at mu minus sigma and mu plus sigma. Well, you can just solve a simple equation to find out the points of inflection, right. Now, let me try to show you here what is the meaning of sigma square. It's obviously you know now that sigma square is going to indicate the variance. So, now you know that if the variance is low, that means there is a higher concentration around the mean value, and if variance is higher, then there is a smaller concentration around the mean value, right. So, in case if you try to plot here the this normal density curve with let us say mean 0, suppose this is here mean 0, and you try to plot here, say here curve number here 1, which is here, curve number here 2, say which is here, and curve number here 3, which is here. So, now you can see here in the curve number 1, the variance is 0.5, in curve number 2 the variance is 1, and in the curve number 3 the variance is 2. So, the value of variance is increasing from curves 1 to 3. Now, if you try to observe this area under the curve number 1 and then try to observe this area under the curve number 2, and after that you try to observe this area curve number 3. So, this area is going to indicate the spread of the values around mean, that is here 0. So, you can see here that in the curve number 1 the spread is less in comparison to the curve number 2 and curve number 3, and similarly the curve number 2 has a smaller spread around 0, that is mean, in comparison to curve number 3. So, this is what we try to indicate through the curve, that a lower sigma, that is the standard deviation, indicates a higher concentration around the mean value mu, and a higher sigma indicates a flatter density. So, this is how the lower and higher values of standard deviations are indicated by this curve. Now, I try to address here a smaller some small issues which are useful in practice as a data scientist. Suppose I try to consider here two types of normal density curve, and their mean and variances are changing. So, first I try to take here two normal curves which have got the same mean. right. So, you can see here this is here the mean equal to 5, and now this is here somewhere here 5, and I try to plot here two possible curves, say at sigma square equal to 1 and sigma square equal to here 4, right. So, you can see here that it is possible that two normal density functions may have same mean, but different variances. This is what you have to observe from here. And in case if you try to look into this figure here, I am trying to take the mean is equal to 15 on the same axis. So, and then if you try to see here, this is here the curve number here, see here, say star. And now if you try to see the same curve with the sigma square equal to 1 is plotted here also. This I try to denote by here double star. Now, can you see that both the curves are identical and they have got the same value of the variance sigma square equal to 1, but their means are different. So, what does this mean? Many times in a real life situation, means I have often heard people getting confused in saying that okay, what is the relationship between the mean and variance, and they try to make different types of a statement. Okay, if the two normal distributions have got same mean, can we say something about their variances, or if they have got the same variances, can we say something about their mean? So, this picture is trying to answer that question, that if you have got two values of variances, you cannot say anything about the mean, or if you know the value of means of the two distribution, you really cannot comment on the variances of the two distribution. These are two different properties, that is what you have to simply understand. Mean is central tendency and sigma square is variability. So, these are the two different characteristics which are trying to characterize the distribution. So, this is how you have to interpret, and do not get confused with these statements. Okay, so now in case if you try to see here that if you try to find out here the CDF of this normal mu sigma square, then suppose x is following the normal mu sigma square, then its CDF is given by here capital Fx, which is minus infinity to x, and here phi t dt. One thing I can show you here, one of the popular notation for indicating the normal density is the small phi, and this Fx that is indicated by capital phi x. That is the very popular notations among the user. You will see that we have got tables for the probabilities for this CDF, and they directly use there the symbol capital phi x. Right. Now, if you try to see, if you want to find out this integral, it is not straightforward. Right, there is no explicit formula to solve this integral, but this has to be solved numerically using some computational methods, numerical methods, and that is why you will find that the probabilities in the format of CDFs are presented in the tables in almost all the statistical books. Right, even there are some books which in the past they were trying to compile only various types of probabilities, and they were trying to compile different types of tables for the probabilities of different types of such distributions. Right. So, now I am going to state here some result which are based on the normal mu sigma square random variable. So, if x is normal with mean mu and variance sigma square, then for any constant a and b, means especially where b is not equal to 0, if you try to define a new random variable as a plus bx, then this new random variable y is also a normal random variable which has got a normal distribution, but its parameters are obtained as follows. Now, you can see whatever the rules you have learned for this expectation and variability, they are going to be useful. So, the mean of y is obtained at expected value of y, which is expected value of a plus bx is a constant. So, expected value of a is a and b is a constant. So, this becomes a b into expected value of x. So, this becomes here a plus b times mu, and its variance of y is given by b square into variance of x, which is b square sigma square. So, you will see that you will try to use such results many times. Now, here comes a very important result, right, that if x is normally distributed with mean mu and variance sigma square, then if you try to define here a new random variable, that means the x minus its mean divided by its standard deviation, that is x minus mu upon sigma. This has got a standard normal distribution 0 1, right, and this is called here as a z transformation, and this random variable indicated by capital Z in general. And you can see here, if you try to find out here expected value of z, this will become expected value of mu upon sigma, which is equal to here 0, because this is mu minus mu, and variance of z will become here variance of x upon sigma square, which is sigma square upon sigma square is equal to here 1. Now, you understand what is the relationship or what is the importance of this result. You are trying to say here that you have got here a random variable x, which is dependent on two parameters mu and sigma square, but now you have got here a new random variable which is obtained by a simple transformation of the normal mu sigma square random variable z, which is also normally distributed, but this has got a mean 0 and variance 1. Now, they are known to us, means in this case when we are trying to say the mean is mu and variance is sigma square, we do not know their values, but in this case when we are trying to say that the distribution is normal 0 1, we know the value of mean and variance. So, this is called as Z transformation. Remember, this is very important and we are going to use it several times, and you will see that in practice, particularly among the users and the applied statistician, they always use the terminology, okay, find out the Z variable, right. So, this result helps in finding different types of probabilities about x in terms of probabilities of Z, right. Now, I just want to show you some results so that you can understand that how are you going to compute different types of probabilities in case of normal distribution. For example, if I say here x is normal with mean mu and variance sigma square, then it is CDF. Now, you know that this capital phi is going to indicate the CDF, which is probability that x less than equal to z, right. So, this is indicated by minus infinity to z phi t dt, where phi is the PDF of normal mu sigma square. That is a standard symbol in the statistics. You will see that many people are using this symbol. So, now in case if you want to find out the value of CDF at minus z, then this is equal to simply here 1 minus phi of z. And if you try to see what is the meaning of this, if you try to understand the meaning, then these results will become very simple to understand. Now, try to look at this normal distribution, normal 0 1. This is the curve of normal 0 1. Here it is somewhere 0. So, minus z is going to be somewhere here, you can see here, right. If you try to see here, this is your here minus z. Now, you are trying to say this is the area between minus infinity to z. So, if you try to see here this area, which I am trying to make as a dots in the red color, and that is going to be the area between minus infinity and minus z, and the total area under the curve, means if you try to see from here, here, that is going to be 1, right. Now, if you try to see what is this area between minus infinity to minus z, this is the complete area whose value here is 1 minus what? Phi of z. What is here phi of z? If you try to take here, plus z is going to be somewhere here, and capital phi of z, that is going to be the area between minus infinity to z. So, that is the area, this one, minus infinity to this point. And you have seen that normal is a symmetric curve. So, if you try to take this area, which now I am going to indicate in orange color, this area and this area on the right hand side, they are going to be the same because the curve is symmetric. So, that is why I can write down here that phi minus z is equal to 1 minus phi of z, or in simple words you can write that phi of minus z plus phi of z is going to be 1 for all values of z. And definitely if you try to find out the value of here say phi of 0, so that is going to be the area between minus infinity to 0, which is half of the curve, which is equal to 0.5. Right. Now, the tables for computation of this CDFs are available, which are trying to tabulate the values of CDF at various values of z, and we can compute them directly into the R software also, but just try to give you a feeling here how these tables look like. For example, if you want to compute here the f of 1.5, then it is going to be the this shaded area between minus infinity to here 1.5, and this area is the area that we want, that we need. And you will see here these tables will look like this one, that on the one column we have the value of here z like a 0, 1 and some more values here, somewhere here 1.5, and then these are here some more values over here for which you can compute the probabilities over directly. But I am not going to explain it here because we are simply going to use the R software to compute any of this probability. That is our objective. Right. Now, I would just want to give you some more information about this normal distribution. If you try to see here, I have taken here different types of color: dark green, light green and lighter green. So, this is here mu, and if you try to take the 2 points on left hand side and right hand side of this mu, they are here mu minus sigma to mu plus sigma. And if you try to see this area, which is indicated by the dark green color, this area is simply going to be the 68% of the total area. And if you try to extend these points more on left hand side and right hand side, and if you try to consider here the values mu minus 2 sigma to mu plus 2 sigma, this area is 95%. And if you try to take out here the further limits between say here mu minus 3 sigma to mu plus 3 sigma, this area is the 99.7% area of the total area. And if you try to see here, I am trying to use here the values mu plus minus sigma, mu plus minus 2 sigma, mu plus minus 3 sigma. If you ever try to deal with the quality control, we have the quality control limits in terms of this sigma limits, or generally you say that people are trying to achieve the 6 sigma limits or 5 sigma limits in their quality control. So, these are those limits. Right. Now, I try to show you here some pictures through which if you try to understand these areas in terms of probabilities, then the life becomes simpler when you try to compute different types of probabilities. One thing, I have prepared this pictures myself. So, yeah, do not go with exactly the same type of shape, because yeah, there can be some difference in the exact value of the shape. So, for example, if you want to compute here probability that z is less than minus a, where is some known quantity greater than 0, and suppose this area here is alpha. So, this is going to be indicated by minus infinity to here minus alpha, and this area here is given by this thing. And similarly, if you want to indicate the area probability that z is greater than or equal to alpha, then this is the area which is going to be there on the right hand side of the curve. So, this area is on the left hand side of the curve, and this area is on the right hand side of the curve. And if you try to compute this area that z lies between minus a and plus a, so this is here minus a and this is here plus a, and you are saying that this area is going to be 1 minus alpha. So, this area here is 1 minus alpha, and if you try to take the same area on both the sides, both this area which is here and which is here, they are going to be alpha by 2, right. So, now you can see here that if you want to compute the probability that z greater than a, that is equal to 1 minus probability of z less than equal to a. So, you can see here probability z greater than a is this area, and this is 1 minus probability that z is less than or equal to small a. So, this area. So, and similarly, if you want to compute the probability that z is greater than minus a, that is going to be the same as probability that z is smaller than a. So, you can see here that this area, that probability is greater than that z is greater than minus a, this is this area, and the probability that z is less than a, this is the same area, right. And similarly, if you want to find out the probability that z is lying between minus a and b are some positive constants. So, that is it, that you know this is a probability z less than b minus probability z less than minus a. So, if you try to see here, you want to compute this probability, this shaded area between minus a and b, and that is going to be this area, that is minus infinity to here b minus infinity to minus a. So, this is the area that you are trying to compute in terms of these graphics, right. And similarly, you can also compute the probabilities in a different way. For example, if your x is following a normal mu sigma square, then you can define here as z, which is x minus mu upon sigma, which is following a normal 0 1. And now, if you try to compute the probability that x less than equal to b, this I can write down here as a probability x minus mu upon sigma, and then on the other side also I try to make the same operation b minus mu upon sigma, and this x minus mu upon sigma is your here z. So, z is less than b minus mu upon sigma. So, if you know the value of b, mu and sigma, you know these values, and then you can compute the CDF at b minus mu upon sigma from the table or from the R software. Similarly, if you want to compute the probability that x is greater than a, this is 1 minus probability of x less than equal to a, which is simply your here. Now, exactly following the same lines, I can write down here 1 minus this phi a minus mu upon sigma, which is the CDF at a minus mu upon sigma. So, you can see here these rules are going to help you a lot. And similarly, if you want to compute the probability that x is lying between small a and small b, I can use the same mathematical formulation here, that you try to write down here a, x and here b, try to subtract in all the values, and then try to divide in all the values by sigma. Then you can have here the same quantity can be written like this, that x minus mu upon sigma is lying between a minus mu upon sigma and b minus mu upon sigma, and this quantity here is z, and you know that this is nothing but your CDF at b minus mu upon sigma minus CDF at a minus mu upon sigma. So, you can compute this probability also. And similarly, if you try to see the probability that x is lying between minus a and plus a, that can be written as CDF at a minus the CDF at minus a, and CDF at minus a is 1 minus CDF at a, and this can be written as twice of phi of a, that is the twice of CD of a minus 1. Now, we come to an end to this lecture, and you can see here I have given you reasonable idea about the normal distribution and how you can compute different types of probabilities, which are really going to be useful. So, my advice to you that at least whatever I have explained you today in terms of computation of different types of probabilities, please try to understand from your heart. Try to understand what they are trying to depict. Once you understand these probabilities through the normal distribution curve, I am promising you finding out different types of probabilities will become very simple, because these probability tables or these different types of probabilities can be computed either directly from the probability or directly from the CDF. So, all these types of manipulation will help you in deciding that how easily you can compute any given probability. So, now I would request you that you please try to have a look in the lecture, try to revise it, try to practice it, and I will see you in the next lecture, where I will try to show you that how to do such manipulation in the R software. So, till then, goodbye.